Good afternoon, IPC students. This is Mrs. Morales. We are starting a new unit on forces. We're going to talk about the forces that actually act upon us and all objects on planet Earth, along with Newton's 3 laws of motion. I'd like to just go ahead and think about what the first slide we have here. We have a school bus. Many of you have ridden on a school bus and can relate with this circumstance, or you've been in a car and you can relate with this circumstance. When a bus that's moving forward applies its brakes, the passengers feel a jerk. In which direction do they feel the jerk? So as you're sitting on the bus or you're sitting in the car, all of a sudden mom or dad or the bus driver doesn't slam on the brakes but does apply the brakes. So their foot goes on the brake and pushes it down. What direction do you move? I'll let you guys think about that for a second. And if you understand how you move, you will move in the forward direction. And that has to do with Newton's first law of motion, that objects in motion will stay in motion until an unbalanced force is applied to it. The unbalanced force in this case was the brakes. So you go in a forward motion. If you slam on the brakes, you're going a forward motion much harder. These are the ideas we're going to start talking about. So let's go to the first slide. I'm talking about forces in motion. Next slide is Newton's laws of motion. We're talking about his first law. I'm just going to go through it and look at it, and then we'll look at it in more detail. It says an object in motion or rest will stay in motion or stay at rest with the same speed. There's your constant velocity that we talked about in the last chapter, and in the same direction until acted on by an outside or unbalanced force. So objects that are just sitting on the table, as you're sitting in your chair, you're perfectly balanced. You're not moving from your position. And this is Newton's first law. It's also called the law of inertia. And we talked about before, inertia is the resistance to move. This is some of you guys, especially on a Saturday morning when you resist moving out of your bed. It's so nice and comfortable to stay in there, and your mass just wants to stay in bed, and it wants to resist motion. So you are balanced perfectly when you are laying in your bed, and the unbalanced force happens when mom and dad encourage you, lovingly, I'm sure, to get out of bed. Now that is a force that you're going to apply to your body to get you out of bed, and then it's going to be unbalanced, and that's the outside force that's acting upon you. Well, the next one, which is Newton's second law. The second law now is your unbalanced force, and this is your acceleration. When an unbalanced force, right here, we got unbalanced force acts on an object, the object will accelerate. Sometimes the acceleration's slow, sometimes it's extremely fast, and it will go in the same direction as the net force. So these are the idea of Newton's second law. So I'll go ahead and get rid of all those. And the third slide is the third law of motion, and it's the law of interaction. Now we're going to talk about how things act when they touch one another. We're going to have two objects that interact. The first object exerts a force on the second object, and the second object exerts a force on the first. Now this sounds really strange, but when two objects touch, they will actually touch each other and the forces will be the same. So the force is equal in strength, but we're coming from opposite directions. Now you guys may have seen this before, is for every action there's an equal and opposite reaction. And I don't know if you remember on your outline we talked about that and how sometimes this can be misleading, and the idea that each object applies a different force upon each object. But that's not exactly accurate. We'll talk more about this later on. Okay, so let me get rid of, whoa, that's not what I wanted to do. We'll figure out how to undo that. Okay, so I just want to get rid of those. Ms. Morales is again learning how to use some more technology as we go along. We're now going to talk about the forces that are acting. Now, you are going to investigate how an object's motion changes only when a net force. You're going to see this word. Oops, I need to grab this and this. We're going to see this idea, net force. Net just means total. all the forces or the total amount of force applied. And sometimes we're going to see that the objects will be balanced or unbalanced. We're going to learn the difference between those two. And we're going to use something new to you guys are called free body diagrams. So, okay, so let's proceed forward and let's go ahead and talk about these. Let's first define what a force is. Many of you, I know in class, if I say what is a force is an interaction. We have to touch. We're going to actually see the difference between a field force and a contact force. But in this case, you're going to feel a push or a pull. And as you can see, we have two individuals here. One is pushing and one is pulling. So as you can see, they are pushing and pulling in the same direction. Do you see those arrows? Both of these arrows right here indicate that they're pushing in the same and pulling in the same direction. So that box there, this box right here, will actually move in the direction of the force. And it's balanced when it's just sitting there, and then when they push and they pull on that box will become unbalanced as it moves. So let me go ahead and get rid of my notes. And so that's the first idea we're going to talk about is force. Now, slide is you saw arrows. These arrows here are going to indicate direction of what we're going. This one, the green one, is going to the right, and the red one is going to the left. Now, if you notice, I want us to notice the size of these arrows here. The red arrow is obviously smaller than and not as long as the green arrow. This is what we're going to call magnitude. Magnitude is size, and magnitude can also be referring to strength of the force. We can see that the green arrow is a stronger force than the red arrow. It's not as strong as a force. So ultimately, what direction would this object end up going in? It would end up going into the right. The red one is going to try to slow us down, but our push or our pull toward the right is overpowering the force that's trying to slow us down or pull us to the left. We're also, so these are, that's your direction. Ultimately, these are going to be called vectors. Vectors have to have magnitude or strength and size, and they have to have direction. So with every answer you're going to be giving now, you're going to need to indicate which direction it's going. We're going to use this letter F for force. And we're going to use a unit for force of a Newton. This is named after Sir Isaac himself. And a Newton, since force is we're going to find out is equal to mass times acceleration, a Newton is going to be kilograms for mass times meters per second squared for acceleration. So this is what a Newton is a kilogram times meters per second squared. Now, I'm very thankful that Newton decided to put his name to this, so we get to use the letter N rather than kilograms times meters per second squared. Okay, so let's go on to our next slide. We're going to talk about two types of forces. We're going to talk about, I'm going to go and we'll go back to our yellow. We're going to talk about field forces, and we're going to talk about contact forces. A field force will act at a distance. Let's just say this is Earth right here. Earth. We do not actually have to be touching Earth. Most of us are on planet Earth, where our dots here are people on planet Earth. We do not actually have to be touching the ground of planet Earth to feel its gravity. We can be way out here in space, and we can still feel Earth's gravity. Earth's gravity will actually reduce the farther we get away from Earth, but it will never get to zero. So the bigger the distance, the smaller the force. The force way out here will be much smaller than it is when you are on planet Earth. On planet Earth, you feel actually a draw toward Earth of 9.8 meters per second squared. We will start using that actually later on in this chapter. And the other force we will have are contact forces. Now you have to have touch. As you can see, our guy here is touching the box. As he's touching the box, he's applying a push or a pull. This time he's doing a push, and he's going to move that box in, looks like that direction. So here are two kinds of forces. Field forces, where you can be in the area of it. The other type of field force we can have is not only gravity, but we can have magnets, and that's the electromagnetic force, which you probably read about in the outline. Magnets, you don't have to actually touch them. In fact, sometimes it's really difficult to touch them because they're repelling or pushing away. Magnets have to just come in the area of, and that's a field force. Okay, let's go ahead and get rid of these notes. Nope, I don't want to do that. Let's see what happens. That got rid of that time. Okay, slide. Now, the first field force we're going to talk about is gravity. So we're going to talk about gravity. Oops. So we're going to talk about gravity. Gravity. So you're going to see a vector image right here. Here's our vector. And as you can see, gravity goes down. It goes down to the center of Earth. So every object actually has a gravitational field force. Oops, I forgot my R. Every object has a gravitational field force. Earth is toward the center of the Earth. So we're going to use an arrow indicating that we go down. It's a good thing we don't go up, because then we would be floating up in the air. But in this case, it'll be down, and we will use the F for force and the G for gravity. Let's see. So you'll call that the force of gravity is what that'll be called. And you'll indicate that the force of gravity is going in the down direction. So, as I said, gravity always points toward the center of another mass. The greater the mass, the stronger the force. Now, we talked about in the book that the sun has an extremely large mass in comparison to the Earth. But because we are closer to planet Earth, we actually feel Earth's gravity more than we feel the sun. So that's here we got the bigger the distance, the weaker the force. So sun's gravity actually gets weaker as we get farther and farther away from it, which is a good thing, because I really don't want to be drawn toward the sun. We would fry up in a hot second. The other thing about gravity, it's always there. So it never goes to zero. It never gets to zero. It gets smaller and smaller and smaller, and it may get closer and closer to zero, but it will never get to the zero. And I'm going to get rid of some of these notes here. I get too many of them. Oh, here we go. And then the same strength between masses. This is Newton's third law of motion. Oops. This is Newton's third law of motion. What causes the gravitational force you feel? Planet Earth. Which way did that force always point for you? It's always going to point down. And do you generate a gravitational force? As you read in the book, yes, you do. What I did with the students in class is I actually walked up right close to a student or two in class and asked, where do they feel my field force when I'm standing closest to them or farther away? And many of them obviously said, of course, standing closest to them, they feel my presence a lot more than when I go farther away. So this is the idea. It's not as if there's a pull, a literal pull, but you do sense presence of people, and that is a gravitational force. Okay, so we'll go ahead and get rid of these notes. Oops, I don't want to do that. Where's my X? Well, I don't know. Oh, I see. There it is. Okay. All right, so let's go to the next. All right, the other field force, which I kind of foreshadowed with you, is the electromagnetic force. Electromagnetic force does not involve masses, it involves charges, and it'll point toward the opposite charge and away from similar. So we have towards opposite charges and then we have away from similar. So for example, let's look at some of these charges. We have a positive charge and we have a negative. Here are your opposite charges. So the idea is a positive charge will be attracted to a negative charge, which is what this is saying right here. And then if we have a positive charge and a positive charge, now we have this similar charge. And they will actually push each other away, which is the idea of repelling. So we have repelling here, and that also applies to negative charges. Two negative charges will actually repel each other too. They'll push each other away. Now, the idea here is the greater the charge, the stronger the force. So for example, if we had a really big plus sign, then we had a really tiny small minus charge. So we have a positive charge on the left and a small negative charge. This positive charge will have a very powerful pull, as it's going to really draw that negative charge toward it. Let me get rid of this. See, there we go. The other idea that I want you guys to get is the same with this same idea applies for field forces, for gravity, or for electromagnetic. The bigger the distance, the much weaker the force. So if I have a positive force charge way out here and it's negative over here, because of this distance in between the two of them, the force will actually be fairly weak. Same idea with two masses of objects. The farther away it gets, the weaker it gets. In fact, this is the number one effect upon either gravity or upon the electromagnetic force. And you might find that, excuse me, that is just my calling your attention to, you might find it in a test question. And just like gravity, it's always there. It gets weaker and weaker. It never gets to zero. So I'm going to write down never zero. And it will have the same strength between charges. If the charges are the same size, like you can kind of see these two right here look like about the same size. These two look about the same size. They will feel the same pull or the same push. So this would be the same pull, and then these two right here would be the same push away. Okay, so let's go ahead and I'll get rid of these notes. And now we're going to talk about the comparison of the two field forces. Field forces always get stronger when objects get closer. And I will be actually sending you guys a cheat card, and that will be on the cheat card. So field forces get stronger as they get closer. So gravity gets stronger and with the more mass. And electromagnetic forces get stronger when the with more charge is involved. But as I said, this you may find on your test. Distance affects field forces with field force magnitude or strength way more than any other factors. So even if the mass is huge, if you get that huge mass like the sun, you can get multiple. I can't remember how many Earths you can get in the sun. Might be something interesting for you guys to look up. If you get, with sun being so far away from us, we are more attracted to the Earth than we are to the sun. And as I said, that is a good thing. Okay, now we'll move on. This one just compares field forces. If you guys have a sticky note, if you have any sticky notes that look like this, if you take one of these off, which I did to the students in class, and I put it on everybody, and I put one on the back of people, you will notice that the sticky note will stay stuck to you, because that sticky note is stuck to you by the electromagnetic force. Now, as you can see, the area between these two trucks is the space between two very large masses, and that would be gravity. We stuck the sticky note on us, and we noticed the sticky note stuck on our clothing by the electromagnetic force. And it stayed stuck on our clothing for a long time. In fact, I kept one on me, and it was on there for about 3 hours before gravity finally took over and it fell to the ground. This is the force of gravity. The force of gravity finally won over the electromagnetic force and pulled it down. So when you're asked which is stronger, the stronger of the two forces is actually the electromagnetic force, which is really interesting. We just proved it with the sticky note. You can take one off, put it on your shirt, and let it sit there and see how long it sits there before gravity finally takes over and it falls. Okay. Now we're going to actually talk about our different contact forces. Now gravity, as we said, the force of gravity is going down. We're going to first discuss the two forces that go in the opposite direction of gravity, and that is going to be Fn, which is the normal force. So it is called the force of normal. And this sounds really strange. It's just the idea that it's the force that's normal to life. I'm not exactly sure why it's named the way it is. That'd be something I'll look up and figure out one day. But it has to have, the force of normal has to have a surface. As you can see, our box is on a table. So the box is on the table, and you can see that the force of normal will work. It's supportive. So that table is supporting that box right here. And it is perpendicular to the surface. If you remember what perpendicular means, if we draw two lines and we put a little box in the corner, that is a right angle. I'll use the angle symbol, and that right angle has a 90-degree size. So that's a 90-degree right angle, and it's perpendicular. And as you can see, the force of normal is perpendicular to the table. So as you're sitting in the chair listening to this, or if you're standing on the floor, your feet and your body, if we drew a line in comparison to the floor would be horizontal and you would be straight up. That would be a perpendicular. I can't even think of the word. You guys would be perpendicular in the direction. So normal forces are always perpendicular to the supportive force. So this is supportive. Oh, IVE, sorry. And also too, the table is on a floor. So if you can see, the table leg is at a right angle to the floor. I'm going to get rid of these notes because there's something else I want to add on to here. Okay, so if we have an object, I'm going to give you a little foreshadowing. If we have an object, I'm going to do a little dot to show that object. So let's say it is you sitting in your chair. I'm going to do a little dot for you sitting in your chair. What force is pulling down on you? And I'm going to use blue, and I'm going to say the force pulling down on you is the force of gravity. And the arrow indicates the direction of the force of gravity. And then I'm going to say, well, since I know you're not falling down, you're able to sit in that chair because that chair is supporting you. You have a force that's going in the opposite direction of gravity. And this is the force of normal. And what's going to be interesting, you're going to see, since you are able to sit in your chair and the force of gravity is not stronger than the force of normal. So gravity is not stronger. These two are actually, and I'm going to show it by a line of congruence, these two are actually equal forces. So I'm going to put in equal here. Since they're equal and you're not falling to the ground and you're not floating up in the air, then that means that these forces, so the force of normal, is actually equal to the force of gravity. And since those forces are equal, that means you are balanced. You're not moving and you're staying in one spot. And I'm really grateful that we have the force of normal, that we have supported surfaces, and we have tables and floors that actually can support us. Otherwise, we'd be pulled through the floor by gravity. Or if the force of normal was stronger, we would actually be floating up in the air. That might be kind of cool for a little while, but may not be what you want to do. It might want, especially if you want to try and walk. Okay, now I'm going to go next force that goes in the opposite direction, and I'd like to focus a little more on this right here, because you can see this is Ft, which is tension. And so Ft means the force of tension. And tension, it's touching. You have a taut rope or string. In this case, you could also have a wire. You could have a chain. As you can see right here, here's our chain or our cord that's holding up that lamp. Now, gravity is pulling down on the lamp into that direction, but the cord is actually pulling it up. And it's attached up here to the roof or the ceiling right there. But this lamp this is like our dot in the middle. And what are the two forces acting on it? The force of gravity. And then because of the cord, it's pulling up, and then it's attached. You actually have equal forces. So we have the force of tension here, and they're equal forces. Gravity is equal to the tension, and we know that because the lamp is not falling and the lamp is not going up. It's actually suspended. Suspended means hanging. And then it's not swinging back and forth. It's suspended, it's hanging in that direction. So we know those forces are equal. And that's a good thing, because if the force of tension was stronger, the lamp would be slowly floating upward. And if the force of gravity were stronger, gravity would be pulling that on that chandelier in the down direction, and you would be pulling that cord out of the ceiling itself. So, and as you can see with tension, it always pulls with the rope. Now let's look at our balloon here. We have a balloon. And in this case, we have the force of tension going in the down direction. Now this is a little more complicated because you also have gravity pulling down, but gravity is pulling down actually upon you, and you are actually holding the balloon. So it's a little bit different because with helium, this balloon has helium in it, and helium's lighter than air, and those are actually some of the principles that we would talk about a little bit more in chemistry. So that's why I wanted to focus in on the lamp. If I demonstrate the force of tension, it will be only with an object being pulled up, not being pulled down. Oh, I want to undo what I just did. I want to get rid of that. Okay, force. The next force we have is friction. Friction here. Friction is a force that needs a surface. It also can cause sliding. Its main responsibility is to slow. It slows because friction will try and resist motion, and that's a good thing. If you've ever been on ice, I've actually, living in California in the mountains, had to walk upon ice. And if you try to walk upon ice, you're not always very effective. Ice is frictionless, and your feet slide because there is a lack of resistance here to the motion, and there's a lack of slowing down. Now, friction is always negative. So what we will put in here is a negative sign in friction. And as you can see, this person here is actually trying to push on this wall. So he's actually applying a force to push on the wall. And his feet, which are on the ground right here, there is a surface, hopefully it's a little bumpy surface, that is slowing his feet and causing and giving a little bit of friction, because you want his feet to slide backwards. That as he pushes forward, friction is going to go in the opposite direction to slow him down. Now, so if the push is the desired direction, this is the desired direction, that's the way we want to go, that would be positive. So the opposite direction would be your negative. That's why friction is always negative, because friction opposes. So friction opposes what direction you want to go. Okay. Let's go to the next one. So now we have, as I foreshadowed a little bit, we have our person pushing on the wall. So here he is pushing on the wall. When you push, you are applying a force. Apply a force. So we have the force applied. So FA stands for force applied. And it's any other push, and it could be a pull. Now, if you grab a hold of your friend's arm and you pull on them, you are applying a push. The main thing with applied force is you have to be touching. It'd be really cool if I could kind of go up to something and say move and not even touch it, and just be use a Jedi force and move it. But we don't have that. That would be really cool. So we have to actually touch an object to apply a force. So if we wanted to draw a force diagram, what we would do is draw a dot for the person. This is the person. And then we would say, what direction is he pushing? He's pushing in that direction, and it's called the force applied. Okay, now we're going to move on, because now I'm going to actually put together, which I've been starting to do. Sometimes you'll have multiple forces. As you can see here, we have two forces. And they're both in the and they're both horizontal. And if we have a horizontal, that is the x-axis. And so we have a person, he's applying a force. So we have the force applied. And the person would like to go in to the right, so that's the positive direction. Now he's got his feet on the floor. Actually, I'm going to circle this in black. He's got his feet on the floor, and the floor has got a little bit of a rough surface. So I'm going to put rough surface equals some friction. And friction is just resistance, which is resistance, I-S-T-A-N-C-E. And you're going to see the force of friction is going opposite the direction that you want to go, so friction would be negative. So I'm going to erase these notes. Whoop. There we go. There. Now, so if I wanted to draw a force diagram, so this is the beginning of what you're going to be doing. If I wanted to draw a force diagram, I would draw a dot in the middle, and the dot is representative of the guy pushing on the wall. Well, what direction is he pushing? He's pushing to the right. Since he is pushing, that is a force applied. So I'm going to say force applied. And that's the direction he wants to go. So I'm going to call that the positive direction. And then because his feet are on the floor and his feet are sliding, but there may be some resistance there, I'm going to call that the force of friction. Now, if you note, the length of this line right here is much longer than the length of that line right there. That's because the force applied is stronger than the force of friction. This is weaker. And we want to add to the force of friction, it's negative. If the force applied is the positive, the force of friction is negative. So so what direction is he moving? Well, if the two arrows were, since the right arrow is longer than the left arrow, the direction of movement or of motion equals to right. And we know that because this arrow is longer. And that's actually the desired direction he wants to go, which is to the right. And that means if the object is moving, it is unbalanced. Okay, let's get rid of some of these notes. Now, as you can see, we move from two forces on the horizontal to two forces on the horizontal and the vertical. And then we also have a force on the vertical. And just to remind you, vertical is this direction and horizontal is like the horizon. It's that direction. Now, the horizontal is also the x-axis and the vertical is the y-axis. Okay, so what is happening here? Let's go ahead and get rid of these notes here. There. Now, what's happening here? We've got someone, again, is pushing on a wall. So he's pushing on the wall. His hands are touching right there, and he is pushing in this direction. So he's pushing. So he has a force applied. Now he's also got a slowing force, and that's your force of friction. So the force applied is the positive, and the force of friction is the negative. They're going in opposite directions. So if we drew a little dot in the middle, there would be our guy pushing on the wall. Now, if you can see, these arrows are about the same length. If they're about the same length, then that means they are equal. So I'm going to do a double line of congruence to say that the force applied is equal to the force of friction. If the force applied is equal to the force of friction, there can either be no movement or constant velocity. The strange thing about force diagrams is if everything is equal on the horizontal side, especially horizontal side, because we're talking about force applied, and we're going to mainly look at it only in the horizontal, which would be to the right or the left. If both of those are equal, then you have either no movement or constant velocity. And remember, constant velocity is it's velocity that's not changing. So let me I just want to get rid of these notes here. Okay, so we know that the force applied is equal to, I want this one here, is equal to the force of friction. We're also going to see something. So we have the guy in the middle. If we're on planet Earth, there is a force that's pulling down on us at all times, and that would be the force of gravity. And as you can see, it's going in the down direction. That makes absolute sense. Now, the guy is on a floor, which equals a surface. And if he's on a surface and he is perpendicular to that surface, then the force that's going against gravity or in the opposite direction as gravity is the force of normal. So now we can see that this arrow and this arrow are the same in length. So they are equal in force to one another. So we could say that the force of normal is equal in strength to the force of gravity. So this means that he's not going in either direction of up or down. He's actually staying in one spot, thankfully. Again, it could be a constant velocity. We could, but we're going to look at it in IPC only as not moving up or not moving down. So as you can see, we have four forces that we're applying here. Okay. Now, as I said to you, I want to just readdress to balanced forces. Balanced forces means, right here, you have the same magnitude, opposite direction. And balanced forces usually will mean you'll have either constant velocity. So if you see constant velocity in a word problem, that means it is balanced. That means not changing. Or you have no movement. It's still. It's still. So you can have either constant velocity or no movement. And that means it's balanced. That means that the net force, or the sum of all the forces, is equal to 0. It's constant motion. It's not speeding up, not slowing down, and it's not changing direction. Now I'm going to talk about a symbol that you see right here. Right here. This symbol here is called the summation symbol. And you're going to start seeing this more often. Sometimes I will write it just kind of like a little squiggly backwards 3. It is the Greek letter for S. In math and science, as you have known, we've done with triangle, there's delta. We've used that before, and that means change in. We will use different symbols to mean different things. You will also use variables to represent vocabulary words. So when we do the summation of symbol, or the Greek letter for S, we are sum means to add the forces. So we're going to add up all the forces together, and that's what the summation symbols means. So if we say the sum of forces, so I'm going to actually erase some of this. I'm going to erase this delta right here. And go ahead and say, so if I say the sum of forces, that also can be sum of forces, or it can be net force. Net and sum mean the same thing. It's all the forces together. So the sum of the forces is 0. So that means there's no speeding up, no slowing down, no changing of direction. And that means it's balanced. Okay, so I'm going to go to the next one. We got to be careful. Okay, that got rid of that. If we have balanced, it will be unbalanced forces. Now we have different magnitudes, opposite directions. So for example, here's our person pushing on the wall. So he's applying a force in this direction. So we have the force applied. And we've got some friction that's trying to slow him down a little bit. And so we have the force of friction. And we know friction is always negative. And this is the desired direction he wants to go. So that since these arrows are unequal in length, as you can see, they're magnitudes or their strengths are not the same, we have movement. So which one, that means one force wins. Which force wins? Well, force applied wins. So the object is moving right. That means the net force is not equal to 0. So we would use the summation symbol, and we do the equal sign, and I put a line directly through it. This means not equal. You might have used that in math already. That means now we have changing motion, which equals acceleration. So anytime you have a problem where something is accelerating, you know it's going to be unbalanced. So acceleration and unbalanced they're directly related. So what's happening? They could be speeding up. It could be slowing down. It also could be changing direction. Okay, now we're going to take these principles and we are going to apply them to some force diagrams. And I will actually be doing a separate, let's see if I can get rid of this. I'll be doing a practice sheet for you guys, like I've done with the graphing, to show you how to do the force diagrams. You can notice the next slide is Newton's second law of motion. So I'm actually going to stop here and record another lesson another time for the second law of motion. Hope you guys have a great rest of your afternoon. If you have any questions, which I am sure you will, please either email me or come to my office hours on Wednesdays or Thursdays. Bye.